last years, and today as Nabil said, I will be talking about the modeling and numerical simulation of the electrical activity of the heart, and we will focus first on the modeling, and then I will give some application. The first one is the application of on electropharmacology, and the second one would be on the inverse problem of electrocardiography. So this would be the plan of the presentation. First, I will give a general context and motivation. Why are we modeling the electrical activity of the heart? I will present the multi-scale modeling in cardiac electrophysiology. I give some numerical methods to simulate electrocardiograms. And then, as I said, we'll give two examples of application. One is the drug effect modeling, and the second one is the ECGI, electrocardiography imaging inverse problem. So the general context, cardiovascular diseases are the most widely killing of people worldwide. Almost 18 million people worldwide are dead because of cardiovascular diseases. They are also in Europe the main cause of mortality, with 4.2 million deaths each year, and they cost a lot of money to the security systems. And this is the World Health Organization statistic. They cause 192 billion per year. So that's why there is a wide range of research in cardiac electrophysiology. Of course, in terms of medical research, on technological research, but also in fundamental science. And in this context, we are working on the numerical simulation. So why numerical simulation? In general, in the world, people are working on numerical simulation because they see it as a powerful tool to understand some phenomena like cardiac arrhythmia, which are not fully understood, and there are too many issues that are misunderstood in the phenomena of the cardiac arrhythmia. A numerical simulation tool could be also a good candidate to build a virtual database that could train medical doctors. And I will give one example in this presentation. At a certain time, I will give an example. And then it could also help to train medical devices, to test medical devices virtually before testing them on real patient. It could be also used, as I will present it, as a tool to predict the toxicity of some treatments. So in terms of, I will give this as like this. So in terms of cardiovascular research system, so the heart, there are too many components in the heart modeling. There is the anatomy, where the people are working on the segmentation, visualization of cardiac structures. This is the anatomical part. There is the electrophysiology, which I will be talking about. There is the solid mechanics, so the heart is a pump, and there is a mechanical phenomena in the heart, and that's also another area of research. There is the blood flow problem with the fluid structure interaction. This is also another area of research. There is the perfusion metabolism, which is the irrigation of the cardiac tissue, which is also another research area. So we will be focusing on cardiac electrophysiology, so the electrical wave in the heart. Why we do that? The first thing that we think that a mathematical model could help to assimilate patient data. So that's what we call personalization, which means that if you have observation, you can fit your model in order to make it behaving like these data. And doing that, you will be assimilating your patient. So this is one of the objectives. once you assimilate a patient, like the model is behaving like the observation, in that case, you can say, my patient is now virtual. I can test many things. I can test therapeutic plans. I can make new diagnosis. I can see more features of the electrical, of the cardiac activity. And in that way, you can, this is the main goal, is to go forward and to make some therapeutic plans and to help medical doctors. So there is a local context in Bordeaux, in especially where I am working here. I am working at INRIA Bordeaux, but it is in the context of IHU Lyrique. So it is an institute between the hospital and university, and it's called Lyrique. And it is one of the investment of the future program, which is promoted by the French government and the French agency of National French Agency of Research, and they choose different centers in France in which there are pioneers in different fields. In Bordeaux, the pioneers are in cardiac surgery and radio frequency ablation. So radio frequency ablation is a technique that is used in order to isolate arrhythmia in the heart by making radio frequency ablation. In Bordeaux, there is a non-invasive cardiac imaging system that has been under assessment in the hospital. And it was an occasion for us to work on this and the data generated by this system in order to test new techniques. Also, we benefit from the fact that the medical doctors here are convinced that the models could help to improve the technology in order to better making of diagnosis and of treatment. There is also in vitro and in vivo and in vitro experiments that are performed in this institute, in the Lyrique, for the validation of methods and also for the testing of the treatment. I'm working at INRIA, and the name of our project is called Carmen, for cardiac electrophysiology, and we are part of this institute. So, in order to talk about the model of the heart, you will see directly that it is a multi-scale model. How you can see that? So there are three main ingredients in order to make the electrocardiography, the electrophysiology from the cell membrane to the body surface. So there is the models at the cellular level, where you will look at the membrane. This is the cellular model, where you will distinguish between intra and extracellular domains. And then there is the tissue level. So we are into the tissue level, piece of cardiac tissue. Then you have an organ level. We are at the organ, at the heart level, and then you are at the body level. And that's where we measure the ECG. The ECG is the main tool, would say the most widely used tool to make the diagnosis of the heart. If you have a heartache, you go to the medical doctor. The first thing that it is measuring an ECG to make a diagnosis. So this is why we are interested to go to the body surface. But in order to generate this electrical wave on the body, there is a phenomena at the cellular level that gives you this electrical activity. So let's see what is the phenomena at the cellular level. We have an extracellular domain and an intracellular domain separated by a membrane, well, what we call the cell membrane. And if you measure the difference of potential between the intra and extracellular potential, you obtain what we call the action potential or the transmembrane potential. Why transmembrane? Because it is the difference between intra and extracellular potential, and the membrane is between them. And if you measure this potential, you look at what happened at the ionic level. There is a migration of when the cell is stimulated. There is a migration of the sodium current, or the sodium, ions, and that makes what we call the depolarization, the wave of activation. And then there is a plateau. This is what you see here. This plateau is the exchange between sodium and potassium and calcium. So here you see the animation. This is the plateau phase, where you see the potassium, this change between potassium and calcium ions. And finally, the repolarization, you have the potassium channels that is open, and you have what we call the potassium current. And these are the main, let's say the main phases of the electrical wave. Well, in order to, I can go further. In order to make a model for this phenomena, you have to look at the behavior of the membrane. So the first thing is that the membrane has a capacitive behavior, and it works as a capacity, as a capacitance. So there is a capacitive current, which is the capacitance times the time derivative of the potential. That gives you the capacitive current. From the other side, since you have a migration of ions between intra and extracellular, you have what we call the ionic current, which is a resistance, which could be modeled in an electrical analog as a resistance. And this way, you can write your balance, the electrical balance on the membrane, and you get this equation. This is the capacitive current, this is the resistive current, and this is the applied current. So you know that now that this resistive current is due to the migration of ions. So there is a model for each of the ion channel that you see here, and that is modeled by this W, and we can suppose that this W is a vector of state variables. And there is a way to see how these ion channels are opened. This has been firstly done by Hodgkin and Huxley, and they have been working on a giant squid nerve cell, and they extract the squid neuronal cell. It is very huge, and they put electrodes inside and outside, and they measure effectively the electrical, the transmembrane potential. And they built the first mathematical model for the electrical activity based on electrophysiological measurement. This has been, they got the Nobel Prize in Physiology and Medicine. And this model is a little bit complex, but it has the main current that we have seen, the sodium current that you see here, what we call, so this is the capacitive. If you give this capacitance here, if you multiply by Cm, all the equation, you see that Cm times dV over dt, that's the capacitive current. And what you see here is the resistive current. And what you see here is the sodium current, the potassium current, and they call it the leakage current, which is the current they couldn't model at that time. So this is the sodium current, and as I told you, there is a unique expression of the gate variable. So here, for instance, for the sodium current, there are two gate variables. One is M and the other one is H, and for each of them, you have the same representation is alpha M times 1 minus M minus beta M. You can expect that there is an exponential representation of this of the activation of the gate variable. You can see it, the same thing for the H, for the gate variable H. We have the same structure of the governing equation, and the same for the n gate variable here for the potassium current. And since this, so you can see this is this is the action potential for the neuronal cell. It's the difference between the electrical potential inside and outside the nerve cell, and it's a spike actually. There is a small what we call plateau. It's directly going to the baseline, and these are the gate variables. This is a simulation of the Hodgkin and Huxley model. So this was the first electrophysiological model. Then people generalized the Hodgkin and the Huxley model in general, and they could add a lot of concentration in the models and a lot of current. You can introduce as many current as you have as gate variables. They added calcium current for different types of calcium current, different types of sodium current, different types of potassium current, and there are some exchangers, and the modeling becomes more and more complex and takes more and more details. But at the end, it's the same formalism as has been presented by Hodgkin and Huxley. So in the literature, you will see, if you look at physiological models of the electrical activity at the cell level, there are too many. They depend on the species, the studied species, because the action potential would change from a species to another. For example, there are some for chick embryo, for guinea pig. This is the most widely, so there are too many models for the guinea pig, and there is a reason for that, that they are used for in pharmacology. There are for rat, for rabbit, for mouse, for human. There are too many models, and each model, you can see the number of equation in each model. So there are models that are very simple, like for 4 variable or 3 variable, and you could have more complex models like this one with the 41 state variable equation, or the O'Hara-Rudy, one of the famous models that has been published in 2011, and it has also 41 state variables describing the concentration, the gate variables, and in details. So that's one way of modeling. There are another way of modeling, which is very simple, and it is phenomenological. It describes just the phenomena with a very small number of parameters. There is the Fichu-Nagumo model, which just follows the Hodgkin and Huxley publication. And then there are also a different version of this Fichu and Nagumo models, which are the Aliev, Panfilov, and Roger-McCulloch models, which are the same. There is a cubic part. You see here V times V minus A, V minus 1. That's for the sodium current, say, and there is a recovery variable, which is W. Recently, also, there is a very famous and too much used by the electrophysiology community, the Mitchell and Schaeffer ionic model, which has only 2 state variables and 5 parameters, and it still have the cubic function on the activation in the ionic current, and a recovery variable, which is here J, and very few parameters. And it's very easy to scale what we call the action potential duration, the duration of the plateau, with the parameters of the model. And that's very easy to calibrate. So that's for the cell model. Now, if you go to the modeling at the tissue scale, if you take a piece of the tissue, you have an intracellular domain, which is in gray, and in blank you have, in white, sorry, you have the extracellular domain. You have the gamma M, which is the membrane, which separates the two domains. And you have UI, which is the potential inside, and UE, the potential outside the cells. VM is still, by definition, the difference between UI and UE, and it's called the transmembrane potential. Sigma I and sigma E are the conductivities of the intra and extracellular domains, and GI and GE are the density current, the current in the intracellular and extracellular domains. So if we suppose that you are in a quasi-static hypothesis, you can suppose that the density of current derives from the potential. That's the Ohm law. That gives you this equation. Ji is equal to minus sigma I, the gradient of the potential in the intracellular domain. And GE, which is the extracellular current, is minus sigma E, gradient of UE. If you suppose that you have the same current, I mean the current flowing from inside the cells to the outside to the extracellular is the same, then you get this equation, which is the conservation law at the membrane. You still have, as we have seen, that this transmembrane current, which is here at the membrane, is equal to a resistive current plus a capacitive current. So that's the way, how we obtain a reaction diffusion model. So we obtain a reaction diffusion model by making an homogenization. So here we are at the organ scale, where we suppose that now, since the cell is 100 micrometer, the size of the cell is 100 micrometer, and we are at the scale of the heart, which is about 10 centimeter. We are 10,000 times higher in scale. We can suppose that omega H is occupied by both the intracellular and extracellular domains. Doing that, you obtain what we call the bidomain equation, which is a reaction diffusion equation coupled to an elliptic one. So the reaction diffusion equation is this one, where you have here the action potential or the transmembrane potential, Vm, resistive current, the diffusion current. This comes from the current at the membrane, and the applied current. This is the balance over the homogenized membrane. Then you have this conservation law, which is the elliptic equation. So you can see here that both are coupled by the intracellular potential here. So these are coupled equation. And you have isolation condition, which means that the current does not flow outside the heart, and the extracellular current does not also flow outside the heart. This is what we call the bidomain model in the human heart. So you can imagine that the conductivities here, the tensors, are anisotropic, and they follow the privileged direction of reaction. It is obtained generally by diffusion tensor imaging, DTI, which gives you the fiber direction of the heart. So if you have opened one heart of a sheep, for instance, one time, you can see the fibrotic muscles, these fibrotic muscles or this fibrotic structure gives you the fiber direction, actually. So there are too many works about the homogenization, Krasovska, Kolifronsoni, and there are also others after that. Now, if you go further, because we say that we want to simulate an electrocardiogram in the body surface, that means that you need the electrical, how the electrical wave is represented in the torso domain. In the torso domain, we suppose that we have a passive conductor. There is no reaction in the torso, and that way you have the diffusion equation, like Laplace equation, but you have still the conductivities here. They could be anisotropic and heterogeneous. And since the body we can suppose that it is isolated from outside, so the current does not flow outside. This is the equation of the electrical wave in the torso domain, where ut is the torso potential and sigma t is the conductivity of the torso. So now we model it from the, let's say, ion channel scale to the body surface scale. So if you look at the model, the fully hard torso coupled problem, you have the bidomain model in which you have the ionic current, the ionic model, sorry, which could be either very detailed, biophysically detailed, or phenomenological model. You have the reaction diffusion bidomain equation, the coupled problem, and you have the torso problem. Now, at the interface between the heart and the torso, you can suppose that you have continuity of potential and current, and then you obtain these coupling conditions. Well, there are studies of the well-posedness of the problem. It is well-posed. We can define a weak solution of the coupled heart-torso problem that verifies the variational formulation of the problem and the initial conditions. And doing that, we can prove the existence and uniqueness of the electrical wave in the heart and in the torso. And in the couplet problem, there are too many studies for that. So if we go to the numerical approximation, you can solve the problem. This is one method. There are too many methods in the literature using either finite difference, either finite volume, or finite element. So this method here that we present is based on finite element, which are piecewise affine finite element discretization in space, and in the time we use a semi-implicit BDF schemes. So in most of all the numerical methods that are presented, we use this kind of semi-implicit. Why? Because the reaction part is nonlinear and is very stiff, and we need for computational issues, we need to explicit these nonlinear terms. And that's why, for instance, here, if you look for, this is the equation for the gate variables, and we need to explicit this part at time n+1. Suppose that you want to compute Vm, the potential and the extracellular potential and the gate variables at time n+1. This is a second order approximation of Vm at time n+1. You introduce that in the nonlinear term and you solve an exponential equation. This would be an exponential equation, and there are very appropriate schemes for that. Then once you have the W, the gate variables, you can inject them. So you computed them, and still you approximate this the torso, the transmembrane potential. Why? Because this ionic current is a nonlinear one, and to solve it in space, so you have a very huge linear problem to solve if you suppose that this is explicit. If it is implicit, then you have a very big nonlinear problem to solve. Now, between the heart and the torso, you have two linear problems here, but they are coupled with the boundary condition or the coupling condition, which are the Neyman boundary condition for the heart and the Dirichlet boundary condition for the torso. You can use a partitioned heart-torso coupling with the Neumann-Dirichlet iteration, you can, so for instance, solve first the torso potential, and then inject the flux into the heart, solve the heart, and then inject the trace of the extracellular potential on the heart, on the torso, and solve the torso, and do it again until you converge. There are too many also in the domain decomposition community, too many methods for handling these iterations. You can also do it monolithically by supposing that your potential U is equal to UE in the heart and UT in the torso. And you suppose, since you have a continuity of potential and current, you can suppose that it's the same field, it's the extracellular potential. And doing that, you take sigma as sigma I plus sigma E, that's in the heart domain, and sigma T in the torso domain. In that way, you can solve the whole linear problem in the heart and the torso in a monolithical way without doing an iteration between the heart and the torso. That means that your linear problem is much more bigger, but it is feasible. And there are many codes that are doing that. Now, once you have your scheme, you make a computational mesh that comes from segmentation of medical images. The segmentation, then you have a triangulation of the surfaces of different organs that you introduce. In the heart, you have to introduce also the fibers in order to introduce the anisotropy of the tissue. And doing that, you obtain, by solving this problem, you obtain what we call the ECG. The ECG here is the difference, what you see as a trace here is the difference of potential between the left and the right hands. And the color that appears here is the transmembrane potential. And what you see on the torso here, it is the extracellular potential and the torso potential on the body surface. So you can compare, once you have simulated, you have your 12 lead ECG, that's the difference of potential between different leads in the body surface. You obtain the 12 leads. These are the 12 that are used by the medical doctors in order to make the diagnosis. You can compare them. If you look at the first ECG, for instance, here, you can see that we have the same waves, but we don't have the same magnitude of these waves. They are all mostly on the right direction, which is a good way to measure the fact that the electrical wave is propagating in the right pattern. Then you can also get more complex geometries, which are physically detailed geometry, and you can see the effect on the ECG here. For instance, the T wave is much more better captured. You can also play with this model. That's why I told you in the beginning that we can make many simulation in order to make different pathological conditions. Here, for instance, you can see a tachycardia, which is here, like here, it's a spiral wave that is propagating and doesn't stop. In general, you have depolarization, repolarization, and then the heart go to rest. There is a rest. In the tachycardia problem, the electrical wave continue traveling around the heart, and that makes the heart beating with a much bigger frequency. And this is one of the pathologies that is very frequent. It's less, it is less dangerous than the cardiac fibrillation, which is an anarchic electrical wave on the heart. So I told you also that it could be used as a medical a tool to train medical doctors. This is a project that we have done with a company called Medicactive, and the project is called Sim for Health. And its object is to make serious games that are used to train either student in the medical school, or also to improve skills for medical doctors that they want to discover new techniques. For instance, in this simulation, we got an image from the ESU, from the CHU de Bordeaux. We segmented the image. We created the geometry of the torso, of the heart, and all the surrounding organs. And we get the necros here. It's a dead area of the heart, we say. And we have the corresponding ECG, and the medical doctors are able to understand this arrhythmia, this pathological condition in the heart. Now we go to the application of the on the drug effect on the ECG. Why is this important? So many proarrhythmic drugs are associated directly with the QT interval on the ECG. So the QT interval, if you want to see it, is the difference between, let's say, it's the time between this, they call it wave, and this wave. So this time, this duration, which is called the QT interval. That's because this is a Q, they call it Q wave, and this is called the T wave. And the time that electrical wave takes from this one to this one is called the QT interval. If that QT is prolonged, that means that the drug is proarrhythmic, and it is not accepted to sell this kind of drugs. So what in the development of a drug, if you, for example, if you look at now the COVID-19 vaccine, there are tests on the QT interval. They have to be sure that this drug does not alter, does not prolong, does not shorten the QT interval. That means that it does not affect the electrical activity of the heart. That's why an ECG simulator is a valuable tool in order to assess the proarrhythmic effect of the drug before going into human testing. And the regulatory agencies, they are interested in silico models, and the FDA now develops a new tool for the in silico assessment of either drugs or also for devices, for medical devices. So let's start from a study by Grandi et al. In 2010. They developed the mathematical models, which contains, I think, about 20 state variable in the cellular model, and they inject in the cell some medical component, which here you can see it is BACL2. They are endophytylite. These are drugs, and they see the effect of the drug on the experimental one. This is the work by Just et al. In human. And in the mathematical model, in the dynamic system, they tested an AK1 or AKR block, and they obtained more or less the same behavior. It's a prolongation of the QT interval. And how they model that? How do they model this this blockage, this introduction of the drug? They, if you remember well, we can go back to the capacitive part. If you multiply this equation by Cm, you get the capacitive current and the resistive current. And then they introduce the model of the drug by modifying the ion channels that are directly affected by the drug. So this Ig is change it from GI times the OG. OG is a function that depends also on other gate variables. And this conductance, what they call this conductance, depends on the drug dose. And they give a Hill equation, which is the original conductance of the drug multiplied by a Hill equation here that introduces the dose. And if you see this, if we take this function only, it has this profile. It's a Hill equation. It has a value of 1 when the drug dose is equal to 0. And it goes to 0 when the drug dose is very high. And when the drug dose is equal to what we call an IC50 value, the IC50 value is the value of the drug dose that half block the current. So the ion channel is blocked by 2, is divided by 2, sorry. So that's one way of introducing the drug. But you can see that this simple way of introducing the drug is very, gives the same phenomena as the experimental one. So if we introduce this into our multi-scale model, we can see these effects that has been observed on the 0D model, but here on the body surface, we can see their effect on the ECG. So we can see that an AKR blocker and potassium blocker prolongs the QT interval, which means that the model is able to capture a pro-arrhythmic drug. I can go very fast on this because it's very technical. And we can see, for instance, on the body surface, how a calcium blocker prolongs this APD, action potential duration, and consequently the QT interval. If we compare both L-type calcium blocker and IKR blocker, one prolongs the QT interval and the other one shortens the QT interval. So you can see that there is an opposite behavior. In that case, if you don't in the component which ion channel is affected, there is an inverse problem here to know which ion channel is blocked in order to make the same QT interval. Here, for instance, between the blue one and the gray line, there are different doses, but we have almost the same QT interval. And this gives the following question, which is an inverse problem in cardiac electropharmacology. If you have a prolongation of a QT interval, which is the ion channel that is responsible of that? So the problem could be formulated mathematically. So there is a fundamental problem, which is the identification. So as I said here, if we have this phenomena of prolongation, we have the question that we want to answer, which ion channel is impacted. And in the model, you see these conductance that are here. So if you look at the multi-scale model, which is a reaction diffusion problem, in the ionic current, which is represented this way, the conductances that generally are affected by the drugs are these parameters, what we call here rho I, for each I, where I is the different ion channel. So the idea of the identifiability here is to identify these parameters. So the question that we raise here, are these parameters identifiable? And for that, we have done a work with people from the Lamsin, with Murad Belaswed, Monsef Mahjoub, and some PhD student, Yassin Abidi, Jamil Al-Aswed, and recently Abir Amri. So under certain regularity of the the model, and if we construct a matrix that is the response of the model to different stimuli, and here the SIL in this matrix are correspond to each column correspond to a different stimulus, different right-hand side, we say, and each line corresponds to the derivative of this ionic current with respect to the parameter number I. If we suppose that the rank of this matrix is different, is full ranked, that's the determinant is different from 0, we can prove under certain regularity that we can obtain generally under a hypothesis on the
Nejib,
yes.
we don't see the slides. It's too small.
Ah.
Yes, your yes.
Do you see now?
It's better. Yes.
So this is the result that we. It's better?
Yes, it's better now.
Yes. So under a certain regularity that, of course, we obtain with the high regularity of the initial condition. We only need to raise the regularity of the initial condition to obtain these C1 in Q the regularity. We can find, and if we have an observation on a small domain of the heart, small heart domain. So here what we call what you see here, W0 here, is a small region of small subdomain of the heart. If we measure the action potential on a small region of the heart, we can control or identify these parameters. So this result is obtained for if we want to measure n parameters, we need n observations. We obtain that by changing the stimulus protocol, the stimulation protocol that satisfies this condition, which is the determinant of the matrix that is composed by the derivative of the current with respect to the parameters is different from 0. There are some issues here. I mean, they are not issue, but they are technically non-possible measurement, because we need to measure the whole state variables in all the domain, and that's not feasible technically. But we can suppose, if we suppose that the heartbeat is periodic, then we can expect that this T0 could be equal to the period, and then we have the measurement as the initial condition. So this could be solved this way. We also improved this model by changing the observation from a subdomain to a subboundary. This is the result in the paper with Abidi et al. And here we have more or less the same result with the more complex model, which is the bidomain model, where our observation is in a subboundary instead of a subdomain. And this is more feasible technically, because when you are in the heart with the catheter, you can measure on the boundary, but you cannot measure inside the heart, although there are some techniques today that allow you to, which are the optical mapping, that allow you to measure electrical information inside the sub-region of the heart. Now, in terms of effective way of estimating these parameters, we formulated the problem as an optimal control problem, where we measure, we want to measure the gap between the model, which here V of rho, These are row bar here is the set of the parameters, and V is the solution of the action of the bidomain model, and we add the regularization, a Tikhonov regularization of this. I think that this could be also simplified. We don't need this term if we have if the hypothesis on the matrix lambda that I showed you before is fulfilled. So it's a constrained optimization problem where V rho here is solution of the PDE problem, which is this one. To solve this problem, minimization problem, we use a descent gradient method, and we need to make a Lagrange formulation of this problem in order to compute the gradient of the cost function. The Lagrangian is nothing but the cost function plus or minus the variational formulation of the problem, where the test functions are the adjoint solutions.
I think we lost Nejib.
Maybe he lost us. Allah يبارك فيه.
Sorry?
قلت لك maybe he lost us. No.
Yes.
الله يجزيه خير. Just to say hello يعني. سلام. الله يجيبه على خير.
We can wait some minutes, 1 or 2 minutes. I think he's almost finished his conference, but
Nabil, the conference is recorded, sir?
Yes.
Yes, okay. So yeah, just a link to the recording, inshallah.